Well, hello, welcome to today's lecture. So we covered 14.1, we covered 14.2, we talked about limits. Now we're going to talk about continuity, this 14.2. Well, let us review a little bit. Let us go back to elementary calculus, what we learned in Math 1A. So we are on 14.2, continuity. Recall. In Calc 1A, we learned that if we have a function or a function like f of x with domain, remember that when you have a function, one of the most important properties of that function is finding the domain of that function with domain. We usually denote the domain of the function with d of f. We say that the function is continuous at a number. Is continuous at, let's say, at a. X equals to a if three conditions are met. So we have to check three different conditions to say that, hey, we have a continuous function. The first one is, first of all, this number is a member of the domain of the function. So a, x equals to a, belongs to the domain of f, is a member of the domain. B, the second condition, the limit of the function exists, limit of function while x approaches a exists, and finally, the limit of the function and y value of the function are the same. Limit of function while x approaches a is nothing but the y value of the function after we substitute a into the function. So you have to check all of these three conditions to make sure your function is continuous. We have the exact same thing, exact same conditions for a function in 2, 3, or more variables. So we say that page 4. Definition, continuity, continuous function. A function in 2 free variables, like f of x and y, is continuous at point, remember that, in one variable you only work with x, one coordinate. Here you have 2 numbers, a point, at a point, like a and b. So your x is a, your y is b. If these conditions are met. First, a and b, this point belongs to the domain of your function. B, the limit of your function while x and y approaches a and b exists. We learned this technique before, different methods to analyze the limit of a function exists. And finally, the limit of the function is equal to the value of the function. In this case, is z value of the function. The limit of function f of x and y while x and y approaches a and b is equal to f of a and B. Three important conditions. Well, let's go over some examples before going over example in two free variables. I'm going to go over one example in one variable function for you. First of all, if you have nice functions, those functions are always continuous. We mentioned that before. Nice functions. Like polynomial functions. Polynomials. Like sine function, cosine function. Sine, cosine, exponential functions. Exponentials and so on, they are continuous everywhere on their domain. These are all continuous on their domain. So how about this function? Suppose you have a rational function, f of x is given as x squared plus 2 divided by x. If somebody asks you, hey, you took Math 1A, you know about elementary calculus? Is this function continuous? If it's continuous, what is the set that the function is continuous on that set? So, where does this function continuous? That's the question. And when you answer that question, you can answer this example as well. Example. Where is the function f of x and y, which is defined as x squared minus y squared over x squared plus y squared continuous? Well, in both cases, you have rational functions. When you have a rational function, you find the domain of the function and you say that, hey, the function is continuous on its domain. Domain of this function is equal to the set of all real numbers. I'm not talking about points. I'm talking about just numbers on x-axis. The set of all x values such that with the condition that, with what condition? The denominator is never 0. The only problem that you have here is the denominator, which can cause problem for you. If the denominator is 0, then remember that we say that it's undefined. So x cannot be 0. Then the function is continuous everywhere. If you don't believe me, you can graph it and actually check the graph of the function. What about your function in two variables? Just a generalization of the concept. You have a rational function. Here you have another rational function. It's rational or quotient function. It's continuous on its domain. This function is continuous on its domain. Okay, what's the domain of the function? Well, the domain of this function is the set of all points x, y, such that, with what condition? We have a rational function. Our only concern is the denominator. We don't want 0 on the denominator. X squared plus y squared cannot be 0, such that with the condition that the denominator x squared plus y squared is never 0. What point make this guy 0? X squared plus y squared is a positive expression. It is 0 if and only if x and y are 0 at the same time. So the domain of this function, if you want to rewrite this and using a different symbols or notations, is going to be r squared, r plus r minus the origin. Let us take a look at the graph. So we have x squared minus y squared divided by x squared plus y squared. Okay, here we go. We have seen this function before. Remember that the limit, we calculated the limit didn't exist near the origin, 0 and 0. So we have to exclude 0 and 0. This is the graph of the function that we saw before. Well, here's a question. We're still on page 4. We're moving on to a different example. We're trying to define a function this way. So let function g of x and y be a piecewise defined function. We define it this way. We say that if x and y is not at the origin, then I have this rational function, x squared minus y squared divided by x squared plus y squared. And if x and y is equal to 0, I'm going to define it to be a constant, which in this case is 0. So what I'm trying to do, I'm trying to somehow include the origin into this function and check the continuity of this function. Is function continuous at the origin at 0 and 0? Continuity, 3 conditions. Let us start checking those conditions. For this function, for function g to be continuous, at 0 and 0, which in this case is your a and b, we must check 3 different conditions. The first one, 0 and 0 must be in the domain of the function. This is your very first condition. Okay, what's the domain of this function? This function is piecewise defined function. On the first piece, you are excluding the origin, 0 and 0. On the second piece, you're actually including 0 and 0 and define function to be just a constant. So, since we defined the function this way, the domain is r squared. How do you see that? You're excluding the origin, And at the same time, you're including the origin with different definitions. So the domain of the function is r squared. All points in xy plane. Everything is included. The first condition is met? Yes. It is true that 0 and 0 doesn't belong to this definition, but 0 and 0 belongs to this, to the second definition of the function. Second condition. So the first condition is met. Second condition says the limit of the function exists. Limit of the function, this is here g. I'm using g, please correct that. Limit of g of x and y, while x and y approaches 0 and 0. It exists. Okay. How do you check that? Last week, we went over a lot of different techniques to actually analyze the limit of the function. Which method you prefer? Should we use just the general path, or do you want us to use polar coordinates? Which one you prefer? So, polar, okay, thank you. Who was that?
It was Sean.
Sean, thank you so much. To check the existence of the limit, we can use polar coordinates. Okay, so x r cosine theta, y is r sine theta. So here we have this function, r squared cosine squared theta minus r squared sine squared theta divided by r squared cosine squared theta plus r squared sine squared theta. And remember that we are taking the limit while we are shrinking our circle. We're shrinking the radius. Okay, perfect. Let us simplify this, and the numerator you can factor out r squared. So we get r squared cosine squared theta minus sine squared theta divided by, let us factor out r squared. So you have r squared and you get 1. And your r goes to 0. Before sending r to 0, we can cancel out r squared and r squared. The limit depends on theta, so it doesn't exist. Since it depends on theta. So is the second condition met? Unfortunately not. Since the second condition is not met, we stop here. We do not need to check the third condition. The third condition, since the second, all three conditions must be true. The first condition is true, the second condition is not true, so you stop. It is not continuous at the troubling point, which is the origin. So one checkpoint for you. Our checkpoint is on page 5. Okay. Checkpoint 1. Here, what's given show that the function is continuous at 0 and 0, so it's continuous on R squared. Show that function f of x and y, you have a piecewise defined function, which is defined this way. On the first piece, you have a rational function. We usually use piecewise defined function if we have trouble having everything in the domain of the function. So x and y is not the origin, x comma y. So in this case, you have 3x squared y divided by x squared plus y squared, and at the origin, you define the function to be 0. There you go. Show that this function is continuous at the troubling point, which is the origin, at the origin. So it is continuous everywhere. R squared. Everywhere, I mean the plane itself, R squared. Okay, so let us solve this. First of all, the first condition is 0 and 0, the troubling point, part of the domain. So 0 and 0 is in the domain of the function. What's the domain of the function? The first part of the domain of the function is this plane that you excluded the origin. And the second part of the function says, hey, now I'm going to define this function at the origin. So I'm filling this gap. I'm filling this hole here. So the domain is R cross R, or R squared, and it includes 0 and 0. You can actually see that here. So, yes. The first condition is met. How about the second condition? Is the limit of f of x and y, while x and y approaches 0 and 0, exists? Which method you use?
I used polar.
Polar, okay. What else? The rest of the class? Which method you used? Use y equals to mx, okay, then?
I used y equals to mx as well.
Okay, how about a squeeze theorem that we did last week? What's the limit in this case?
0.
0, very good. So, to analyze the limit, existence of the limit of the function, we can apply different methods. So for the limit of this function, we can use A. Use a general path, y equals to mx. B, polar coordinates, why not? X equals to r cosine theta, y equals to r sine theta, and the most important one that guarantees the limit to be 0 is the method that we used in Calc 1A, elementary calculus, squeeze theorem. We also went over a similar example last week on Wednesday, squeeze or sandwich theorem. By applying the squeeze theorem, it assures you that the limit of this function is nothing but 0. Yes, and the limit of a function f of x and y, while x and y approaches 0 and 0, is nothing but 0. Your z is approaching to 0. And C, the last condition, is the limit of the function while x and y approaches 0 and 0 equals to f of 0 and 0, the limit of the function is 0. The z value of the function at 0 and 0 is also 0. 0 is equal to 0, so all conditions are met. The troubling point, we don't have any problem with that. the function is continuous at 0 and 0, so the function is continuous everywhere. So you can write the conclusion here. Since the function is continuous at the troubling point 0 and 0. Why I'm saying it's a troubling point? Well, because it's a rational function. The only problem you have is with the denominator. The denominator cannot be 0. Look like you only have 1 point. You don't have to worry about the rest of the points. It's going to be just the origin. Since the function is continuous at the origin, so it is continuous everywhere r cross r or r squared. Here we go. Very well. Let us start 14.3, partial derivatives. So first of all, before talking about the tricks and shortcuts in finding partial derivatives, there is an official definition of partial derivatives, which has to do with the limits of this quotient function. So we define the partial derivative of function here on page 1. Here on page 1. Definition. The partial derivatives of function, suppose you have a function in 2 variables, f of x and y, is defined this way. So the partial derivative of function f with respect to the first variable. So think about it this way. You're actually calculating the average rate of change of the function with respect to variable x. And now that you're taking the limit, it's going to be instantaneous rate of change of the function with respect to variable x. It's the limit of f of, okay, suppose you're taking this partial derivative when x and y are getting closer and closer to a and b. So let's use f of x, a and b, f of a plus h, comma, b minus f of a, comma, b divided by h while h approaches 0. If this limit exists, then you're good with the partial derivative of the function with respect to variable x. H is a variable which is very small. It's getting closer and closer to 0. The same with partial derivative of function with respect to second variable y at a and b, which is defined as the limit of f of a, comma, b plus k minus f of a and b divided by k. Again, k is a variable which is getting closer and closer to 0. Officially, when you're talking about partial derivatives, you're talking about these limits. If these limits exist, then we have some nice shortcuts to actually take the partial derivatives of the function. Well, so still on page 1, note that for nice functions. Again, remember that. If you have nice functions, your life is easy. Your calculation is super smooth. Nice functions like polynomials, sine, cosine, and so on. We listed them before. The limit exists everywhere. So we're not worried about the limit definition of partial derivatives. These limits exist. So we only apply shortcuts. What do I mean by shortcuts? Suppose you have a function like f of x and y. This is coming from your math 1a. This is what we call equals to, let's say you have 2xy. What's the partial derivative of f with respect to x? Remember that. When you're taking the partial derivative of f with respect to x, it means that the second variable, y variable, is just a constant. So you're taking the derivative of this expression with respect to variable x. The derivative of x is equal to 1. So you have 2 times 1 times y, which is 2y. The same with taking the partial derivative with respect to y. X is fixed. X is fixed. You're taking the derivative with respect to y. The derivative of y is 1. So you get 2x times 1 or 2x. The exact same shortcuts that you learned in Calc 1A or elementary calculus. Very well, here we go. We are on page 1, going over our example. Example. So here we have this function. Our function is given as f of x and y equals to x squared y to the 5th. Question says, hey, find the partial derivative of f with respect to x, partial derivative of f with respect to y. So we are actually looking for instantaneous rate of change of the function in the direction of x-axis, then in the direction of y-axis. Do we have a nice function? This is a polynomial function. In 2 variables. So we can directly apply the shortcuts that we learned before to find f of x. Remember that f of x can be denoted by partial derivative of f with respect to x. We fix the second variable, which is y. So here you have x squared y to the 5th. Y is just a constant. You can assume it's just a number. You are taking the derivative with respect to x. The derivative of x squared is 2x. So f of x, or partial derivative of f with respect to x, is 2x, the derivative of x squared, and copy down y to the 5th. Now, to find partial derivative of f with respect to y, or partial derivative of f with respect to variable y, we fix our first variable, which is x. Well, taking the derivative with respect to y, the second variable, it means that this guy is just a constant, it's just a number. So when you take the derivative with respect to y, it is 5 y to the 4th multiplied by x squared. So you copy down your x squared, 5y to the 4th. Let us move on to the next page, page 2, go over another example. So 14.3, page 2, another example for you. In this example, another really nice function is given. Let f of x and y be equal to, let's see, x cubed plus x squared y cubed minus 2y squared is given. Again, you have a polynomial function in two variables. Question says, find partial derivative of f with respect to x at point 2 and 1, and also partial derivative of f with respect to y at the same point 2 and 1. What are the slopes at these points? Since we have polynomial function, you can just do the shortcut to find partial derivative of f with respect to x, which is partial derivative of f with respect to x. We just fix the second variable or y. The derivative of x cubed is 3x squared. We have addition. The derivative of x squared is 2x. It also has y cubed, so we copy down y cubed. This guy is a constant. The derivative of constant is 0 minus 0. Now, the partial derivative of f with respect to x at point 2 and 1. It means that your x is 2, your y is 1. Just do the substitution. You get 3 to the square plus 2 times 2 times 1 cubed. So we have 12 plus 4, which is 16. Instantaneous rate of change with respect to x at this point is positive. So it's going to be increasing. Now, partial derivative of f with respect to y, which is partial derivative of f with respect to y. Now you fix your x. Your first expression is just a constant. It's going to be 0. The derivative of the constant is 0. Plus addition. X squared is just a constant, so we're going to copy down x squared. The derivative of y cubed is 3y squared minus 2 times 2, 4y. Well, question says find the partial derivative of f with respect to y at this point. So, partial derivative of f, 2, 1. So your x is 2, your y is 1. You get 2 squared times 3 times 1 squared minus 4 times 1. 12 minus 4, which is 8. So both of these slopes are positive slopes. So the rate of change for both of them with respect to x, with respect to y, are going to be increasing and positive. Okay, guys, let's go over shape points. So you can practice a little bit. 2 checkpoints for you. Very well. So the first checkpoint, checkpoint 1, you have this function. You have a trig function. F of x and y is given as sine of x divided by 1 plus y. And the question says find partial derivative of f with respect to x and find partial derivative of f with respect to y. And the second checkpoint, checkpoint 2, your function is actually another trig function. It says find the partial derivative of this function, sine of x squared y to the 5th with respect to x. Very well. As you all mentioned, to find the derivative of the function with respect to x or y, you have to apply the chain rule. Since you have sine of a function u, if you have u of x, if you remember what you learned in elementary calculus, and when you want to take the derivative of composition of 2 functions, it is equals to u prime times cosine ux, chain rule. So very well, here you have x divided by 1 plus y, and you are taking the derivative with respect to x. It means that your y is a constant. So it's like saying that, hey, I have x divided by a constant, and I want to take the derivative of x over 1 plus y. So this is equal to x over 1 plus y, taking the derivative with respect to x. You can write it this way, prime adjustment, since you have different variables. You have the partial derivative with respect to x of this quantity inside the parentheses times cosine of x over 1 plus y. What's the derivative of x divided by a constant? It's just a constant. So it's going to be 1 divided by, this is the derivative of x, which is 1, divided by the constant 1 plus y times cosine of x over 1 plus y. Now you're taking the derivative of the quantity inside parentheses with respect to y. Very well. So here you have the partial derivative with respect to y, x over 1 plus y times the same cosine of x over 1 plus y. Okay, for this part, you can either use the rational rule that you learned before, or you can just say that, hey, this is 1 plus y, so I'm going to write it on the numerator with negative exponent and then take the derivative. So here you have x times 1 plus y, the negative exponent, and I'm taking the partial derivative of this with respect to y, multiplied by cosine of x divided by 1 plus y. So here you have an exponent, the derivative of the quantity raised to an exponent. You drop the exponent, -1, negative, you have x, and 1 plus y to -2. And remember that the derivative of 1 is 0. The derivative of y is equal to 1 times cosine of x over 1 plus y. So you can simplify this and write it as minus x divided by 1 plus y squared cosine of x over 1 plus y. The same process. The partial derivative of f with respect to x. Here you have to apply chain rule again. Since we are taking the derivative with respect to x, it means that our y is a constant. So the derivative of x squared is 2x. Don't forget to copy down the quantity that is multiplied by y to the fifth. And the derivative of sine is just cosine. And you have to copy down the quantity. That's it. Very well. So I expect you to ask, well, Professor, you took the derivative with respect to x, you took the derivative with respect to y. Now you're creating some new functions. Can we take the partial derivative of these new functions? Of course. You can continue this process. Since you have new functions, you can take the partial derivatives of these functions and actually define the second partial derivatives of the original function. There you go. So on page 3, we're going to talk about the second partial derivatives, and you can generalize the idea to the third partial derivatives, to the fourth partial derivatives, or to the n partial derivatives. So page 3, the second partial derivatives. Remember that it's like taking the second derivative of a function in elementary calculus to understand the concavity of your function. Is it concave up? Is it concave down? So we need these information later on. We're going to use these for optimization and actually finding the maximum, minimum, maximum volume, minimum loss, and more applied stuff in calculus. So the second partial derivatives are defined as follows. Okay, so suppose you have partial derivative of f with respect to x. For this one, you can take the second partial derivative of function with respect to variable x, or you can take it with respect to variable y. So first, you have to find the partial derivative with respect to x, then take the second partial derivative of the function with respect to x. We denote it this way, f of x and x. So let me write it here so you know that this is the black color. F of x is referring to the quantity inside parentheses. So we take the inside partial derivative, then this x on the other side actually showing this outer partial derivative. If you have the partial derivative of f with respect to x, and take the second partial derivative with respect to y. Of course, why not? Which is equal to. So f of x, which is the inside function. Now you take the partial derivative with respect to y. We can continue this process. Suppose you have the partial derivative of the function with respect to y. Now you can take the second partial derivative of the function with respect to x, which is equal to f of y x. So the ordering is important. Which one comes first? You have partial derivative of function with respect to y. Now you take the second partial derivative of the function with respect to y again, which is equal to f of y and y. So we can write them this way. Let me just list all of them here for you on the right-hand side, so we can go over examples on the left-hand side. In summary, f of x and x is equal to the partial derivative of f with respect to x. Then you take the second partial derivative of f with respect to x. There we go. So these are the symbols they use to represent the second partial derivative of the function. F of x and y is the partial derivative of f with respect to x. Then you take the partial derivative with respect to y. Another notation for this, on x. Then f of y and x, of course you have to switch these. Second partial derivative of the function with respect to y, then with respect to x, and finally f of y and y, which is the second partial derivative of the function with respect to y, and we have this guy here. Let us go over some examples. Still on page 3. Example. Find the second partial derivatives of the following function. So here you have f of x and y equals to. What do we have here? We have x cubed plus, you have x squared y cubed minus 2y squared. There you go. So first, we need to find the first partial derivative of this function with respect to x, with respect to y. So we need f of x first. It means that our y is just a constant. So here you have 3x squared plus 2x y cubed. Okay, you have your first derivative. Now you can take the derivative of f of x with respect to x. So let me write it here. So you're taking the derivative, partial derivative of the first partial derivative with respect to x. It means that again your y is just a constant. The derivative of 3x squared is equal to 6x plus 2. The derivative of 2x is 2, and you copy down y cubed. So this is f of xx. Now f of x, y, or the second partial derivative of the function with respect to yx. So you're taking the partial derivative of first partial derivative, which was with respect to x. Now you're taking this derivative with respect to y. It means that your x is a constant. The derivative of 3x squared is 0 plus the derivative of y cubed is 3y squared, so 2x, 3y squared. This is equal to 6x y squared. Very well. How about f of y? F of y, we take the first partial derivative of the function with respect to y. It means that your x is a constant. You get 0 plus 3 get x squared 3y squared minus 4y. Now we're using f of y to find the rest of the second partial derivatives. Here we go. F of x, f of yx, f of yx, which is equal to partial derivative of x for this function. You're taking the partial derivative with respect to x. It means that your y is just a constant. Okay, so in this case, you're taking the partial derivative with respect to x, which is 2x 3y squared, and this guy is 0. Which is equal to 6x y squared. And finally, the second partial derivative of the function with respect to y is equal to, you are taking the partial derivative of f of y with respect to y. It means that your x is a constant. Here you have 6x squared y minus 4. Well, in differential equations, there is an important function that we call a harmonic function. This is our last page on 14.3. So in differential equation, we have a function that we call harmonic function. A function u of x and y is called a harmonic function if it satisfies this equation. The second partial derivative of the function with respect to x plus the second partial derivative of the function with respect to y, if you find these two functions, add them together, this is actually equal to 0. This equation is met, then you say u of x and y is a harmonic function. Give us an example. Okay, let us go over one example together. Show that u of x and y, a function in two variables, like e to the x sine y is a harmonic function. If you're wondering what's the name of this equation is called Laplace equation. Laplace equation. Well, to show that this is a harmonic function or satisfies that equation, Laplace equation, we need to find the second derivatives of this function. So we need ux, then we need the second derivative of the function with respect to x. We also need u of y and the second derivative of the function with respect to y. Then you're taking the partial derivative with respect to x. This is equal to, so here you have product of two functions. One of them has x in it, the other one has a y in it. So you're lucky. When you're taking the derivative with respect to x, this guy, sine of y, is just a constant. The derivative of e to the x is e to the x. So we get e to the x times sine y. Now we're using this function to find the second derivative with respect to x. The same argument. Here you have e to the x, y is a constant, so sine y is a constant. E to the x, the derivative is e to the x times sine y. The first part of this equation is here. E to the x sine y plus. Now we need to find the second part of this equation. What's the derivative of the function with respect to y? It means that your x is a constant. So you are only taking the derivative of sine y, which is cosine y. This is e to the x cosine y. Now, we take the second derivative of the function with respect to y. E to the x is a constant. The derivative of cosine y is minus sine y. Very well. So you get negative e to the x sine y. Well, I have plus minus e to the x sine y. They are opposite of each other. The outcome is equal to 0.